You walk past a downtown bank built before 1915, limestone facade, heavy cornice, copper roofline. You look up and spot a roofline tower, a short mast with radial arms and ceramic standoff insulators, the kind you have seen on old utility hardware. You have been told it is just decoration or just a lightning rod. But decoration does not need insulators, and a simple lightning rod does not need multiple isolated conductors running in parallel. You follow the metal down the parapet and find repeating clamp scars and symmetrical mounting points, as if the building was designed to carry a rooted system, not a single spike. So why does a non-functional ornament have isolation hardware, distribution symmetry, and standardized attachment geometry? Here is the contradiction. Either the labels are wrong, or the building is hiding an obsolete utility layer in plain sight. I promise the traces are still visible, the documentation exists, and you can verify both today. Stand on the corner and scan the roofline of any loop-era commercial block built between 1895 and 1910. Focus on the banks and the counterhall districts where money moved and prestige mattered. You will see it, a short mast rising from the parapet, maybe 4 feet tall, topped with radial arms spreading outward like skeletal branches. Bolted to each arm are porcelain or ceramic standoff insulators, the white glazed kind that utility crews mounted on telegraph poles. Green patina copper runs nearby along the coping. Ask anyone today and they will tell you it is decorative, a Victorian flourish, maybe a lightning rod if they are being technical. But look closer at those ceramic standoffs. They are designed to isolate conductors, to prevent electrical contact between metal elements. A simple lightning rod uses one dominant down conductor, a thick cable dropping straight to a ground rod. This rooftop hardware has multiple isolated runs, parallel paths, symmetrical distribution. Period electrical supply catalogues from the 1890s list these components under roof terminals and atmospheric apparatus, not architectural ornament. Count the conductors if you can get a clear view, usually 3 to 6, each on its own insulator, each routed separately down the building face. If it is a lightning rod, where is the single dominant down conductor? The answer is that you will not find one because what you are looking at is not lightning protection. Move to a hotel built before 1920, one of those heavy masonry buildings with a pronounced parapet and metal coping along the roofline. Stand back and study the parapet edge in afternoon light. You will notice repeating dark marks, shadows where metal once pressed against stone, oxidation halos around former contact points. These are not random. They follow a straight line along the coping, spaced at regular intervals. The repeating pattern is visible across the length of the roofline. Measure the spacing if you can. In most buildings from this era, you will find mounting points every 6 to 8 feet. The bolt holes are still there, often patched over, but visible as filled circles in the masonry. The pattern is too regular to be aesthetic, too consistent across different architects to be coincidental. Compare this building to another before 1920, 2 blocks away. Different architect, different owner, different facade style. But the clamp spacing along the parapet is nearly identical. 6-foot intervals, same bolt configuration, same height above the roofline. That is not artistic preference, that is adherence to a specification. The weathering patterns tell another story. Where metal clamps once sat, you see accelerated oxidation, the characteristic green-blue of copper corrosion. These are not the marks of occasional decorative brackets. They are evidence of long-term contact, year after year, of expansion and contraction, metal conducting current and heat in ways that left chemical signatures in the stone. Why do different architects repeat the same attachment geometry? Because they were following installation standards for functional systems, not inventing decorative schemes. Now follow one of those conductor paths inward. Choose a municipal building from the early 1900s where you can access the top floor. Look for sealed wall penetrations near the roofline, usually within 10 feet of the parapet. You will find them, circular patches in the masonry, sometimes covered with matching stone or stucco, but dimensionally distinct from windows or vent openings. Get close enough and you will notice ceramic bushings at some entry points, white or brown glazed insulation still embedded in the wall. Building codes from 1895 through 1920 required ceramic or porcelain insulation at any point where conductors entered a structure, specifically to prevent fire hazard and maintain isolation. Trace the path inside if the building allows access. You will find abandoned conduit chases running vertically from these upper floor penetrations down toward basement levels. The chases are sealed now, but their geometry is still visible, boxed out channels in the plaster, sometimes with remnant metal raceway brackets still bolted to studs. This is where the idea that they are just decoration falls apart. Decorative elements terminate at the building envelope. They do not penetrate through protected bushings into interior chases. Period electrical codes list these requirements explicitly. The 1897 National Electric Code specifies that all conductors entering buildings shall be protected by approved insulating bushings. Look for patched holes aligned vertically with rooftop hardware. In many buildings, they line up almost perfectly: a rooftop terminal, a wall penetration 20 feet below a chase running down to basement utility spaces. If nothing was being carried inside, why route anything through protected bushings? Expand your survey across building types within a single metro region. Focus on the construction boom between 1885 and 1915, when urban cores filled with banks, hotels, factories, and rail depots. Walk through the downtown district with your eyes on the roof lines. The pattern repeats: the same terminals, the same insulated arms, copper strips running along the coping, and distinct nodes at parapet corners. Banks built before 1890 almost universally show rooftop apparatus on their highest points, usually above vaults or main banking halls. Hotels at the turn of the century placed them on corners and along ridge lines. Factories from 1900 to 1915 mount them near skylight monitors. The placement is not random. It follows building geometry, specifically targeting high points and edges where atmospheric potential gradients would be strongest. If you are systematic, build a photo grid. Corners, ridges, and highest points, the same positions recur across building types and architectural styles. A bank designed by one firm and a hotel by another show identical node placement relative to roof geometry. Pay particular attention to corners where placement repeats most clearly. Here is the question: why do corner nodes appear exactly where electrical potential gradients would be strongest? At corners and edges, the difference in atmospheric potential between ground and elevation becomes most pronounced. If you were designing a system to collect atmospheric charge, you would place receiving nodes precisely where these buildings place their ornamental terminals. The copper strips along coping lines reinforce the pattern. Copper is an excellent conductor, resistant to corrosion, and period building codes specify it for long-term atmospheric exposure where conductivity must be maintained. You will find these strips running between nodes, connecting terminal points into a networked system. The pattern follows physics and roof geometry, not ornament tradition. Step inside an office block constructed before 1920, the kind with a marble lobby and a rear service core. Make your way to the basement or top floor mechanical spaces. Look at the walls in these utility areas. Specifically look for rectangular shadow outlines where large metal cabinets once mounted, the cabinet footprint left on the wall. You will find bolt patterns in the masonry, 4 or 6 anchor points outlining a cabinet footprint. Often there is discoloration where metal backboards pressed against the wall for decades. Measure the spacing, typically 3 to 5 feet wide and 4 to 6 feet tall, positioned at chest height for operator access. Sometimes you will find remnants, fused disconnect switches still bolted in place, labeled plate screw holes where manufacturer tags once identified the apparatus, and heavy gauge conduit stubs entering from above or below. The infrastructure is distribution scale, designed to handle multiple circuits and regulatory control. Procurement records occasionally survive in building archives. They list hardware, insulators, wire, clamps, terminals, meters. One invoice from 1907 for a Chicago office building itemizes atmospheric collection apparatus, complete installation, with line items for roof terminals, copper conductor, porcelain standoffs, and regulation cabinets. Measure the bolt spacing if the mounting points are still visible. Compare it to catalog standards from the era. Electrical equipment manufacturers published standardized cabinet dimensions. You will find matches. The footprint corresponds to regulation and distribution cabinets designed for multi-circuit control. The cabinet geometry tells you that whatever system this served required control and aggregation, not just a passive connection. The placement near both roof chases and distribution points suggests a mediating function. Something came down from above, was regulated or stored here, then distributed outward. What was regulated here if not just a single line? The mounting evidence points toward aggregation and distribution. Trace conduit paths in a factory loft building from the 1910s, particularly on the top floor near skylight monitors. You will notice something unusual. Conduit runs go upward first, then branch downward. Standard electrical distribution flows from the service entrance to endpoints, typically running down from utility connections. These runs go the opposite direction. Look at how these conduits mount. They use insulated hangers, ceramic or porcelain supports that isolate the raceway from structural contact. Period installation manuals specify this detail for conductors carrying atmospheric or collected charge, distinguishing them from standard building wiring. Find the junction points where these upward chases branch. You will see junction box scars near roof beams, rectangular outlines where metal boxes once connected vertical and horizontal conduit. The branching geometry suggests collection at roof level with secondary distribution below. Stand directly under one of these chases and look up. In many buildings, you can trace a straight line from the chase to a sealed roof penetration, and from that penetration to an exterior roof terminal. The alignment is precise, not approximate, and deliberately straight. That precision requires intentional design. Why route to the roof if the roof feature is meaningless? Standard electrical service enters at grade or basement level, rises through vertical chases, and branches horizontally to floors. This system does the opposite, originating at the roof and feeding downward. That inverted logic makes sense only if something functional existed at roof level that required collection and distribution. Compare this to buildings with conventional electrical service from the same era. The difference in routing logic is immediate and unmistakable. Conventional service flows one direction, this flows another. Two systems, two sources, two purposes, and only one remains connected. Focus on 3 anchor sites visible from street level in a typical downtown core built between 1890 and 1915. First, a commercial bank, 5-story, with rooftop terminals positioned above the vault. Second, a residential hotel, 8-story, with terminals at every major roof break. Third, a municipal hall, with terminals crowning the highest wing. All 3 share a consistent hardware vocabulary, the same insulator types, similar terminal shapes, copper coping conductors, and sealed wall penetrations. These are not obscure buildings, they are prominent structures on major streets passed by thousands daily. The hardware is visible, ceramic standoffs catch the afternoon sun, copper patina contrasts with limestone, and terminal silhouettes break the roofline. Yet almost no one registers them as anything but architectural detail. City permit archives sometimes preserve approval records. Search permits by building name and date range, filtering for roof work and electrical apparatus. You will find entries that read permit for installation of atmospheric collection apparatus and approval for roof-mounted terminals and associated interior equipment. The administrative language treats these installations as standard building systems requiring municipal approval. The wording is revealing. Permits do not describe ornamental metalwork. They use apparatus terminology, equipment language, not architectural language. The permits specify materials, copper conductors and porcelain insulators, installation requirements for isolation from structure and approved grounding, and inspection schedules. This vocabulary makes the function clear. What is striking is the shared timeline. Permit dates cluster between 1890 and 1915, with very few installations after 1920. The adoption curve shows a clear rise, peak and decline, exactly what you would expect from a technology cycle, not a decorative tradition. Architectural ornament does not appear and disappear in a 25-year window. If permits called it apparatus, why did later histories call it ornament? The relabeling happened gradually as systems were decommissioned and their function forgotten. A defined adoption window suggests a technology cycle, not timeless decoration. Consider what records must exist if this infrastructure was functional. Start with insurance requirements. Fire underwriters in the years from 1890 through 1915 documented any electrical apparatus, potential ignition sources, and fire spread pathways. Search historical insurance archives and you will find references to roof-mounted atmospheric apparatus in building surveys. Underwriters Laboratories Guidance from 1905 discusses inspection criteria for auxiliary electrical systems employing atmospheric collection, specifying requirements for insulation, grounding, and interior protection. Fire safety bulletins reference roof conductors and terminals explicitly, distinguishing them from lightning protection by noting their branching interior distribution. Equipment catalogs provide another documentation layer. Manufacturers sold atmospheric collection apparatus as complete systems including terminals, conductors, insulators, regulation cabinets and meters. A 1908 electrical supply catalogue lists atmospheric collection terminals for installation on commercial buildings, hotels and public structures, complete with porcelain standoffs, copper conductors, grounding hardware and regulation equipment. Prices and shipping weights are listed. Here is the key question. If this was about safety, why do we see distribution like branching inside buildings? Pure lightning protection consolidates current to ground. It does not distribute it to interior circuits. The architectural evidence shows branching, regulation equipment, and distribution panels. That geometry makes sense only for a system that used the collected charge, not just dissipated it safely. The distinction matters. Safety documentation often preserves the original vocabulary even when function gets rebranded. That persistence helps us reconnect the visible hardware with its historical purpose. The insurance bulletins, fire codes, and inspection protocols locked in terminology, apparatus, collection, distribution, which later generations reinterpreted without understanding the original meaning. Reconstruct the system from components visible and documented. Start at the roof. Terminals with radial arms positioned at high points served as collection nodes positioned where atmospheric electrical potential concentrates. The insulators isolate each conductor, preventing current from shorting between channels. Follow the conductors down through sealed wall penetrations, each protected by ceramic bushings as codes required. Inside, the routing leads to a regulation cabinet. This is where raw collected charge would need conversion to usable voltage and current. Period patents describe voltage regulation apparatus for atmospheric electrical systems, typically employing resistance banks and circuit protection. The branching distribution from these cabinets suggests localized use, rather than whole building power. Realistic applications for intermittent low-power supplemental electricity include indicator lamps in vaults or stairwells, charging storage batteries for emergency lighting, powering low-current instruments, and supplementing conventional service during off-peak demand. Trade journal articles from 1895 through 1915 discuss these applications specifically. Engineering publications reference auxiliary atmospheric systems for supplemental building electrical requirements, often noting their utility where continuous high power is not necessary, but cost reduction or operational redundancy has value. Patent filings provide technical detail. Multiple patents from 1890 to 1910 describe methods for collecting and regulating atmospheric charge, including circuit topologies for voltage regulation and distribution. The diagrams match the architectural evidence: roof terminals, insulated conductors, regulation equipment, distribution branches. Museum collections sometimes preserve complete apparatus examples. The Smithsonian and Technical Museums in Chicago hold roof terminals and regulation equipment from this period donated from demolished buildings. These physical artifacts confirm catalog descriptions. They are real manufactured products installed in quantity and documented in use. The system operated within known constraints. It was not free energy, it was supplemental, intermittent, maintenance-heavy infrastructure that worked only under favorable atmospheric conditions. The components tell the story: collection, isolation, regulation, distribution. Examine why the surviving hardware looks the way it does. Look at the copper conductors where they are still visible. They are heavy gauge, substantially thicker than you would need for simple lightning protection. The material choice, copper rather than cheaper iron, reflects specific requirements: high conductivity, corrosion resistance, and long-term durability in exposed conditions. The ceramic insulators are similarly overbuilt. They are substantial components, often 4 to 6 inches in diameter, with deep weathering grooves and robust mounting hardware. Period electrical codes emphasized isolation integrity for atmospheric systems, requiring insulators rated for outdoor exposure, temperature cycling, and moisture resistance. Insulators were specified to withstand the elements. Trace the conductor runs where they are visible along parapets. Notice how they follow short, direct paths with frequent standoff mounting. Electrical installation manuals specified maximum unsupported conductor spans, typically 6 to 8 feet, to prevent mechanical stress and maintain consistent isolation. The mounting points you see are not aesthetic choices, they are code compliance. Look at how weathering has affected the components. Ceramic insulators persist largely intact. Glazed porcelain resists environmental degradation remarkably well. Copper conductors show green patina but retain structural integrity after a century. This hardware was built to last because maintenance access after installation was difficult and expensive. Weathering patterns tell a maintenance story. The weathering patterns themselves provide evidence of function. Where copper conductors contacted stone, you see characteristic green oxidation halos, evidence of electrical current flow that accelerated electrochemical corrosion. Where insulators mounted, you find clean contact zones. The ceramic prevented conductive contact and thus shows no corrosion transfer. Oxidation halos and clean contact zones point toward deliberate electrical design and long-term operation. Why do we often find the shell but not the guts? The answer is economic. Exterior hardware was difficult to remove and had limited salvage value. Copper conductors were worth recycling if they were accessible, but rooftop work was dangerous. Interior components, regulation cabinets, meters, and switches were easily accessible and had substantial material value. They were stripped during modernizations, while exterior apparatus stayed in place. Track the decommissioning sequence through its physical traces. In buildings renovated between 1920 and 1940, you will find missing cabinet doors with hinge marks still visible, conductor ends cut cleanly rather than corroded through, chases patched with newer materials, and meter mounting points with screw holes, but no corrosion signatures. Renovation specifications sometimes survive in architectural archives. A 1928 modernization plan for a Chicago office building includes a line item listing removal of obsolete atmospheric apparatus, capping roof penetrations, disconnecting interior distribution, and salvaging copper conductor where accessible. The language is matter-of-fact, routine infrastructure removal during electrical service upgrades. Maintenance memos from this transition period revealed the reasoning. One 1925 memo from a hotel manager notes that atmospheric collection apparatus was no longer maintained. Utility electrical service was now reliable and cost-effective. The manager recommended removal of interior equipment and noted that exterior hardware may remain if removal cost exceeded salvage value. The physical sequence is consistent across buildings. First, meters and regulation equipment were removed because these had immediate salvage value. Second, interior distribution panels and conductors were disconnected. Third, accessible copper conductors were removed. Finally, roof terminals were either removed if easy to reach or abandoned in place when removal required expensive rooftop work. This pattern explains why so much exterior hardware survives while interior components vanished. The cost-benefit calculation favored removing valuable, accessible interior equipment and leaving difficult-to-reach exterior apparatus. Over time, the surviving exterior hardware, stripped of function and context, was relabeled as decoration. Here is the relabeling mechanism. Building surveyors in the 1930s and the 1940s encountered roof terminals and insulators with no obvious function. Interior equipment was gone, and documentation had been filed away or lost. Without functional context, surveyors labeled visible hardware as ornamental metalwork, architectural detail, or period styling. Relabeling reduced liability and simplified building histories. The administrative path of least resistance led to systematic reinterpretation. Understand why atmospheric collection systems faded through simple economics and standardization. By 1920, utility electrical service had matured dramatically. Grid power became reliable, affordable, and available throughout urban cores. Infrastructure investments in generation and distribution made utility service overwhelmingly superior, with no weather dependency, no maintenance burden, and no operational complexity. Reliability was the decisive factor. Compare the cost curves. Operating an atmospheric collection system required ongoing maintenance, including cleaning insulators, inspecting connections, replacing corroded components, monitoring regulation equipment, and repairing weather damage. Utility electrical service eliminated all of this. 1 meter and 1 bill produced a predictable monthly cost. The reliability difference was decisive. Atmospheric systems worked inconsistently, depending on weather conditions and atmospheric phenomena that nobody could predict. Utility service worked consistently, providing stable voltage and current independent of environmental factors. For commercial buildings with paying tenants, that reliability premium was worth any cost difference. Consistency determined choices. Standardization drove the final shift. By 1925, electrical codes had consolidated around utility grid service as the normative power source. New construction codes assumed grid connection, and equipment manufacturers optimized products for grid-compatible specifications. Atmospheric collection systems became orphaned technology, with no code support, limited equipment availability, and no inspector familiarity. Standardization sealed the transition. The technology was not suppressed, it was simply outcompeted. Grid electrical service delivered better performance at lower operational cost, with higher reliability and standardized support. Building owners made rational choices to decommission systems that provided marginal supplemental benefit and required substantial maintenance. Outcompeted describes the process. If the replacement is obvious once explained, why do the old traces still confuse us? Because the remaining parts look decorative once their counterparts are removed. Roof terminals without interior equipment resemble ornamental finials. Conductors without functional endpoints look like decorative metalwork. The components make sense only when seen as parts of a complete system, and that system now exists only in fragments. Decorative is the misleading impression. Return to that bank built before 1915, where this investigation began. The rooftop tower is still there, silhouetted against the sky. The ceramic standoff insulators catch afternoon light the same way, white glaze contrasting with green copper patina. Nothing has changed except your ability to read what you are seeing. Perception has shifted. Before it was decoration, an architectural flourish, perhaps a lightning rod. Now you can see it as a receiving node positioned at the building's highest point to collect atmospheric charge. Insulated conductors routed that charge through sealed wall penetrations to interior regulation equipment, where it supplemented conventional electrical service for low-power applications. The same physical object reinterpreted through evidence. Look at the sealed wall penetration visible from the street. Behind that patch, ceramic bushings sit. Follow the implied path downward through interior spaces with vertical chases running to basement utility spaces, cabinet mounting points where regulation equipment once controlled voltage and current, and distribution branches feeding out to local circuits. Those traces are subtle, but they map a working system. The empty cabinet footprints still exist inside. Those rectangular bolt patterns mark where apparatus once regulated the collected charge. The hardware is gone, stripped for salvage value during renovations, and the mounting points remain. Absence is evidence. Systematic removal is confirmation of function. Archive collections hold the documentation. Municipal permits describing atmospheric collection apparatus, manufacturer catalogues listing complete systems, and patent filings diagramming collection and distribution circuits. The paper trail is extensive once you know where to look. The building has not changed. You have. You can now distinguish between true ornament and orphaned infrastructure, between decorative metalwork and decommissioned utility systems. Walk past any commercial building built before 1915 and you will see these traces. They are not hidden, they are visible, documented, verifiable. What other ornaments are actually endpoints to systems we stopped teaching? Obsolete does not mean imaginary. It means a better alternative one, and the old layer stayed visible.